Good afternoon. My talk today is going to deal with water, energy, and the food nexus as a comparison between the humid Caribbean and the arid MENA region. Human population has vastly outstripped the availability of water in the world. My talk today is going to deal with how we use the water, food nexus, and reuse water. As a comparison between the humid Caribbean, the areas of arid greatest concern today for water human population has vastly outstripped the availability of water in the world. My talk today is going to deal with how we use the water, food nexus, and mountainous areas in South America. As a comparison between the humid Caribbean, the way that I areas of the greatest concern today water nexus, and the nexus consists of three pillars that are important for sustaining societies: food, water, and energy. Now, if you overuse one of these, you get a little bit of imbalance in the three-legged stool. However, you can get collapse of the stool if you do total overuse of any of these resources. Our approach has been to prepare a modified nexus in which we consider that water, food, and energy join together in the center to affect human health, but the whole process is surrounded by the economy. Economics determines how you're going to be using each of the components of the nexus. What I have here is a model of how we approach each nation, and the white indicates how much of water, energy, and food is available, and the hashed or the dark gives you an indication of how much for that country is being used. For example, in this one, they're using 70% of their available water. Adaptive management is the key to sustainability. You must be able to rebalance the stool, to change the importance of water, especially for reuse for multiple purposes. The multiple factors that are responsible for the current problems are population, agriculture, and climate change. I'll start with the Middle East and North Africa, the MENA area, as an example of the dry region sustainability. One of the biggest problems in this area is the total overuse of the aquifer system, to the point of they no longer have sufficient water. This is ancient water, and we're not being able to use it because it's been used improperly in the past. One thing that popped out in our studies was looking at water security, and there are three levels. You have water stress on a regular basis, chronic stress of water on a daily basis, and absolute water scarcity. If you consider the countries that are in the absolute water scarcity, it's surprising that there are a few island countries in the Caribbean that have lots of water, but yet they're absolute stress. So today I'm trying to contrast between these two types of systems. Water per person per year in the Middle East and North Africa is vastly different between Iraq, Iran. Syria had lots of water. Morocco has water. Egypt has water. But then we vastly decline very rapidly. The one approach that I started in doing is looking for the countries that have failed, in which the stool has collapsed in the nexus of sustainability. The first was that of Somalia, in which you overused the water, agriculture collapsed, society collapsed. We all know that story. The second is Yemen. Obviously, Yemen is going through a major war right now. They have lost their water. It's controlled by the Houthis. That was obvious. Syria is on the list because it just went through its own civil war, and we have major water loss. And finally, we have to predict which countries will be next. And sadly, I put Jordan on this list. Now let's examine this. Water use in Jordan throughout and the rest of the Middle East has been primarily for agriculture. And in the case of Yemen, it's not used for food, it's used for the production of khat, which is a narcotic. So we're using we're using water incorrectly. We're using it for agriculture more so than domestic. Turning to Yemen, it was the former breadbasket of the Middle East. It had over 10 times the amount of arable land than any other country in the area. But by the 1960s, it began to import most of its food. It had lost the capacity to produce food. That is a direct result of drought, urbanization, where people are leaving farms, and especially new technology where they began to drill more boreholes and to shift to very inefficient irrigation methods. End result, collapse. The gradient in the nexus conditions of the Middle East, Jordan uses 20 years of groundwater annually. That takes 20 years of accumulation. It has no water, little energy, but yet it has a desire for agriculture. Saudi Arabia is losing and lost its groundwater and its springs. It has lots of energy, and it has a desire for agriculture. Contrasted with Oman, which has reasonable amounts of water, little energy, and a desire for agriculture. Let's contrast these. Irrigated land in Saudi Arabia has declined steadily from the 1990s. In the 1990s, Saudi Arabia was the 5th largest exporter of wheat in the world, and now they're importing most of their food. Our studies have worked since the 1990s looking at springs in Saudi Arabia. Saudi Arabia had 46 springs in 1990. It declined to 14 springs in 2007. And when we went back, we only found 11 springs in 2018, but that included 2 new springs, all because over-extraction of groundwater. This work, if you want to download these 2 works, they were done by my PhD and master student, Kamal Al-Jahani, and this is some of the best work done on the importance of springs in the Middle East. The final thing is looking at Jordan. Jordan used all of its available water, but it has to have a water supply because you have refugees from Palestine, Syria, and so the Red Dead project is letting water flow from the Red Sea by gravity down Wadi Araba to the area of the Dead Sea where it's desalinated and pumped into the mountains of Oman. This is absolutely not sustainable. It's a short-term gap, but you have no power, you have no water. Jordan is in big trouble. So in the Middle East and North Africa, we have had a shift from water sources from surface waters, springs, to groundwater aquifers, which were overpumped, and finally a reliance on desalination. But the trend is to use more and more energy just to get water. We have to find a way to reuse the water and use it efficiently. Desalination plants are obviously everywhere throughout the Gulf, as well as in Saudi Arabia, but you're producing very expensive water that's pumped many kilometers to where it's needed. The ongoing, one of the biggest problems that we've had in the Middle East is drought, a series of droughts. Here's an example from 2008, where we had a regional drought that went right across Iraq, Iran, southern Turkey, which is the source of water for Syria and Iraq. But we've had a whole series of these, and Yemen. Looking at Syria, in just 3 years, the amount of irrigated land totally collapsed in Syria, and we can't go back to it because once you stop farming, the desert will encroach, and it's darn near impossible to reclaim those areas. Water security promotes political and social security, and the real poster child of this is Syria. If you look at the drought from 2005 to 2010, you can see that Syria got in big trouble, and this is just prior to the uprisings of 2011. So a number of people have said that the loss of agriculture, movement of people to cities, have promoted social unrest, which led to political unrest. Now, I want to contrast this with the Caribbean. So in the case of the Middle East, we have energy, but we don't have resources. In the case of the Caribbean, we have resources, but we have no energy. And so let's look at the difference. Our study looked at 20 small island developing states in the Caribbean and looked at them because some of them import all their water and energy. Agricultural production does not meet population needs. Projected climate change is forecast for decreased rainfall. And tourism is now the main driver of the economy. What does tourism bring? It brings more use of resources. It brings more people for a limited resource. But it supplies the only money that is available for the production of water. Most people in the Caribbean have access to energy. However, very little of it is renewable. It relied on oil, most of which is imported from the United States. Not sustainable at all, because you must have money to buy the oil, and that money must come from tourism. Most of the countries of the Caribbean are not malnourished, but many are in danger. And so we're at the point that we have to be very careful of making sure that just the basic dietary needs of the people are met. Water use in the Caribbean islands is lower than what's available to it, with the exception of Barbados and St. Kitts and Nevis, which were on that list, by the way, of severe water shortage. They're overusing the water available to them. That said, the amount of water, even though they're not using what's available to them, the real problem is that most of these countries are in danger of severe water scarcity, and with projected increases in climate change leading to less rainfall, it's only going to get progressively worse. In summary for the Middle East, in summary for the Caribbean, we see all of them fail for food. So that leg of the stool is completely gone. The stool is falling over, but yet energy, most of them don't have energy, and half of them don't have water, which is surprising because this is an area of high rainfall. And when you contrast it to MENA, you have areas that they should not be losing water. When you do a change in the tourism, this is a national model that we made for Barbados, you see that currently 25% of the economy is based on tourism, but it implies it provides employment, but it uses valuable resources. And what we're trying to figure out, is tourism a negative or a positive? And I know that Saudi Arabia is considering increasing the tourism section as well. And what does this mean? We need to have some kind of a nexus model for that. So the work that we're doing now is to determine if there's a critical island size below which it is impossible to have a sustainable nexus. And we're now looking at Dominican Republic, Cuba, and Puerto Rico in this regard, and I can report on that at a later date. So we have a number of things that are going on right now, this past month, that have really come to the news and said that we are at a critical point where water sustainability is collapsing globally. We're looking at a series of areas in the world which are focal points for water production. 1, Central Europe and the Alps. 2, the Himalayas. 3, South America. And as you can see from this, we've had a major loss of glaciers in all of these areas since 1970. Looking at the Alps of Switzerland especially are the production zone for the Rhone, the Rhine, the Danube, and the Po. But yet the Swiss glaciers are absolutely disappearing. And we're losing the source of the water to these major rivers. But turning to an area where I've been working extensively, and that's the Andes, all the Andean countries are losing their glaciers. The glaciers not only form the Amazon, but they are critical, especially in Bolivia, where I'm going to give an example. I work in the El Alto region in Bolivia, which is an area that's losing its glaciers, but below the glaciers, they have produced over the years a series of reservoirs to trap water that in turn can be used for the farmers in the highlands, as well as the city of La Paz. But these areas are drying up because the glaciers are disappearing. This has resulted in water conflict, both in La Paz and in the indigenous people areas in the mountains where they're producing quinoa. So you've got urban versus rural. What it led to was social unrest and political change. President Morales was replaced as a result of no water. The next place, the last example I'll talk about, are the Himalayas and the high mountain areas of there. It's the source of the Ganges, it's the source of the Brahmaputra, And it's interesting that Nepal made a lot of money by having a whole series of dams right below these glaciers where they are able to produce hydroelectric and sell it to India. Unfortunately, the glaciers are melting rapidly and we're in trouble. The Himalayas, they're really taking innovative ways of trying to trap as much water as they can before it gets away. So in one case, they have something they have created called artificial glaciers, where they'll take melt water from the glacier and put it into an area where it can freeze and then slowly melt to be used by the local farmers. They've also produced these stupa, which are put a pipe up, send up water, it creates a dome, and again, you are storing water in the short term. This is not a solution. This is only to get you through the next few years. In February, last month, there was a major disaster in the Himalayas where you had the collapse of a glacier. It ended, it didn't exist anymore. And when it collapsed, it ended up destroying one of the reservoirs below it that was used for hydroelectric. And you see a picture on the left, which is the dam before, the dam during the flood, and what was left afterwards. This is only the beginning. It's the tip of the iceberg, pardon the pun. The second thing that's going on was also in February. This is very close to me. There's a small town called Oldsmar, which is part of Tampa. I live in Tampa. And a hacker got into the computer system at the water supply system and increased sodium hydroxide from 100 parts per million to 11,000 parts per million. Luckily, it was caught immediately. But the problem is we now have the ability of hacking in. Anybody in the world can hack into water supply systems and poison entire population. So not only do we have a water problem, we have a major hacking problem. And Saudi is not immune from that because you have just single distribution lines that go to the major. So in summary of this, nexus instability leads to social and economic instability, leads to political instability, leads to society collapse. And this happens in both dry and wet countries. But we have to figure out ways to reuse water, to use it more efficiently. And one of the ways is through green infrastructure, which can be owned by the local community. Unlike traditional engineering, these are natural systems that can go on forever. Some examples in urban areas for green infrastructure are provided here, but how to design with nature to keep the water and not just put it out into the desert or to release it downstream. One of the things that has great benefit for MENA would be the benefits of urban green roofs, which can be used to produce food, to reduce energy use in buildings. Someone told me the last time I was in Riyadh that, oh no, it's too hot here. But no, that's not the case. These things can be built in all climates. Here are examples from the Middle East, from UAE, in which you can take the water from people's sinks, not their toilets, but their sinks, pump it up onto the roof, and you can use it to have gardens and to grow crops. An example of this, my final slide, is that of urban agriculture. The example is Mexico City, which is dry, very dry. It has 9.4 million people, and currently 20% of the food of Mexico City comes from urban and rooftop gardens, and that was in 2012. Thank you for your time, and I appreciate you inviting me. Thank you.
Hello, everybody. My name is Howard Wheater. I'm going to talk today about hydrological modeling for water resources management in arid areas. It's a very great pleasure to be speaking to this meeting. I was awarded the Prince Sultan bin Abdulaziz Prize in 2006. It was a great honor, and I've also been privileged to serve on the Prize Council since that time. And I'd like to pay tribute to Prince Sultan bin Abdulaziz for his inspiration in developing the prize, and for his memory, which continues, and for his son, Prince Khalid, who continues to give great leadership to this program. So I'm going to take you back to work that I was doing in Saudi Arabia a long time ago in the 1980s to address some issues around water management in arid and semi-arid areas. These are the regions of the world, as we all know, where water is most scarce and most precious. But what we often fail to remember is that the hydrology of these areas is really very different from humid zone hydrology. And there are challenges of scientific understanding and major challenges of modeling. In most of the world, in humid areas, we use hydrological models routinely for many purposes: flood forecasting, water resources design, water resources management, coupled modeling of different kinds, linking with sediments and water quality and ecosystems. But most of the models that are used are really not well suited to application to arid areas, because there are particular challenges and particular difficulties which yet have to be overcome. So I'm going to really present those challenges and talk to you a little bit about the way forward. So one question is, how useful are hydrological models for arid and semi-arid areas? And another question, what are the future needs and challenges to improve our capability for managing water in these areas? So one of the main challenges of arid areas is limitations of data and limitations of detailed studies. There's one watershed in the world which is famous. It's called Walnut Gulch. It's in the south of Arizona, and that's been monitored for well over 50 years now as an experimental basin. And there really is nothing to match that anywhere else in the world. But in the 1980s, I was privileged to be part of a representative basin study in the southwest of Saudi Arabia. This was a pioneering initiative that studied 5 basins ranging in size from 500 to 5,000 square kilometers. And it was funded by the then Ministry of Agriculture and Water. I think it's an important study and one that's played an important role, but I'm going to argue at the end that we really need more studies of this kind to bring this work up to date. So this is a very beautiful part of the world, as many of you will know. We have mountains draining towards the Red Sea, and the traditional use of water resources is to tap the groundwater that's in the Wadi alluvium. And you can see the bottom picture, a traditional well, which is located in the bed of a Wadi alluvial system. So a few important points about this study. First of all, we had 100 rain gauges spread over these basins. Each basin had a very detailed weather station, as you can see in the second picture. There were many flow stations and groundwater observation wells. And the picture on the right is an interesting one, because you'll see that there's a float recorder located at a very great height above the bed. And that's because the first time this instrument was installed, it was washed away by a flood that came down this normally dry channel of around about 3,000 cubic meters per second. That's a huge amount of water coming down the system. So that tells us that floods in these areas are important, but they're also potentially very dangerous and very damaging. And in the flood season, it's common for people to suffer damage, and sadly sometimes for there to be loss of life. Another important aspect of this study was that each of these 5 basins had permanent teams of observers living in the basin, and that was really crucial to data quality. So various things can be rather simply shown from this work. I'll just show you a few photographs. First of all, when we have intense rainfall, we get very extensive generation of overland flow. This happens very rarely in other parts of the world. Obviously, for urban areas, we get a lot of overland flow, but to have such extensive overland flow is not common, and it gives a very rapid response. Another important aspect is that we've got intense rainfall falling on bare soils, and those soils tend to crust and give us more runoff than we would expect. And then we have flash floods being generated. And this is an interesting picture because if you look at the sky, you can see that we have a clear sky, cloudless, and yet we have a flood wave moving down this dry Wadi bed. And I'll just show it progressing down the system at roughly a jogging pace. So this is the nature of the water resource, because this flow infiltrates into the Wadi bed, and that provides groundwater, which can be used for a variety of purposes. And the bigger the flow, the further it travels before it infiltrates. And this flow characteristic gives us a major challenge, because when we measure flow at a gauging point, we don't actually know how much water has traveled upstream. In fact, we may have no flow observed because all of the upstream flow has infiltrated. So this is a big challenge for interpreting flow data. This slide shows the processes of channel bed infiltration. This is at the end of a storm, the end of a flow. You can see there's quite an extensive flow in a large channel. But if we dig a little pit next to this flowing channel, it's unsaturated. So what we see is that this flow, which is on a very permeable substrate of Wadi alluvium, is actually perched. And if you look carefully at the photograph, you can see there's a layer of sediment that's been deposited, and this is maintaining that flow. So after a day or so, this flow will dry up, the temperatures will rise, the fine sediments will dry out, crack, and then disperse, and then we'll be back to a permeable channel. So if we do measurements of the permeability of this channel bed under dry conditions, it will be very high. And yet you can see that towards the end of this flow period, we have this perched water flowing. So there's some important issues around the interaction between surface flows and groundwater recharge, which still are not well understood. I'm going to turn now to rainfall, because that's a major issue for these areas. So this is a picture which shows snapshots of sequential hours of rainfall in a basin called Wadi al-Leith. It's about 3,000 square kilometers. And the first hour is in the top left, and then the second hour, and the third hour, and the fourth hour. And you can see that most of the rainfalls recorded as 0, but in the first hour, there's a burst of rain at the top right hand of the diagram, the northeast corner, up to 17 millimeters in an hour. The second hour has very little rain. The third hour has a burst of rain in the center of the catchment, again up to 19 millimeters. And then the fourth hour is dissipating. So we have a very, very spotty picture captured in the daily summary. So the order of half of these rain gauges observed no rainfall. So this is one of the major challenges for us in trying to model this system. It's not uncommon for rain to fall between rain gauges. You have no rainfall observed, and you have a significant flow. And that's a real challenge for any hydrological modeling. This is a diagram that shows response of one of these basins moving from the top of the basin to the bottom. And we can see groundwater levels and some surface flows. And at the top, we have a distinct rise in April, as you can see, of groundwater level. But if we move down to the bottom of the catchment, there is no response apparent in that groundwater system. So we can take groundwater measurements at the base at the bottom end of this Wadi system, and apparently see no record of the recharge that's taken place upstream. So it's not only surface flows that are problematic, we also have to think very carefully about groundwater data. And then there are some little conundrums. So this is a diagram that plots total rainfall volume for a set of storms against the total runoff volume. And if you look carefully at this diagram, you can see that the largest runoff volume comes from one of the smallest rainfall volumes. So this is again because the rain gauge network, although quite dense by conventional standards, is failing to capture the precipitation in its full spatial extent. So we have a set of really critical process issues which are very problematic and difficult to address. First of all, extreme spatial variability of precipitation. I've shown that here. If you look at the literature from Walnut Gulch, you can see it even more dramatically. Secondly, we have these runoff generation processes. So extensive overland flow can occur, but crusting can affect the soil properties, give us more runoff than we think. We've got these complicated processes of losses of flow to the channel bed, which we can call transmission losses. They're affected by all sorts of factors. We tried to measure this in the field. When people have put instrumentation into the field, it's usually lost because the floods are so damaging. The floods mobilize the sediment in the bed. But as we've seen on the recession of the hydrograph, as the flood is passing, we get this deposition of fine sediments. So it's a very complicated set of processes which determine how much water is recharged to groundwater. And then the groundwater recharge itself, of course, depends on the subsurface topography. And I've done work based on the Saudi data that shows the effect of lenses and layering in the alluvium, the legacy of previous floods, and how that affects the recharge process. So there's a set of real challenges there, and we still don't have a lot of good science to really understand and quantify some of the processes at small and also at large scales. I'm going to very briefly take you to the Sultanate of Oman and a little study that illustrates some of these, modeling a flood response in Wadi Ahin. This is a wadi that's quite small, it's 800 square kilometers, had a major flood, as you can see. It flows from the mountains to the Gulf, to the Batinat Plain. So this was some work done by Aisha Al-Qureshi, who was a PhD student of mine and a director of the Ministry of Water Resources in the Sultanate. So we worked with a model called Kinneros, which is one of the few models in the world that's really been specifically designed for arid areas. It's developed by the US Department of Agriculture, David Woolheiser. We had data from 29 events. So here's an aerial shot of the catchment. The right-hand diagram at the top shows us the distribution of rain gauges, which is really quite dense by any standard. The bottom left-hand side shows us how the Kinneros model operates. It represents the catchment as a series of plains which can infiltrate and generate overland flow, and that feeds a set of channels which can generate runoff and also infiltrate. And on the bottom right, we can see how the catchment is split up. So the first thing to note is that even with this network of rain gauges, how we represent the spatial rainfall makes a huge difference to the modeling. So what we see here are different ways of interpolating the rainfall, and they give very different modeling results. This is a particular event, and we can fit a model to overland flow, to peak flow, or we can fit a model to the runoff volume. We get different parameters and slightly different results. But the bottom diagram here is probably the most interesting, because here we've got the best parameter sets taken from each of the 28 events and applied to this particular event of the 11th of March. And you can see how different the results are. So it's very difficult to get a representative set of parameters, really because of these problems mainly to do with spatial rainfall. And here is a diagram that shows the performance fitting to minimize the difference of the observed and simulated flood peak and difference between observed and simulated flood volume for each of these events. And there are different strategies for selecting best parameter sets. And if you take the ensemble average of the best parameters for each individual event, you can get wildly inaccurate results for some. And really what we did here was take the best parameter set fitted to all of these events. However, if we look at the data, there's some interesting effects that are apparent. So the top left diagram shows the flow volume plotted against the total rainfall, and it's a tight relationship. And similarly, the second left the diagram below that shows the flow peak plotted against total rainfall, and again, it's quite a tight relationship. So simple regression does quite a good job, really better than a distributed hydrological model in representing the relationship between peak flow runoff volume and rainfall volume. So there's some important lessons to be learned here about the use of models and the use of basic data analysis. So just to make some concluding observations, water resource management and water management, flood management also in arid areas is a huge challenge. We need hydrological models. What I've tried to show in this very short talk is that modeling is really a very difficult challenge. There's a lot of work needed to improve our scientific understanding of these processes and to develop appropriate models and modeling systems, and particularly handling this issue of spatial rainfall. We have to think very carefully about that and think about using stochastic methods that can represent the uncertainty in the spatial rainfall. So we need, first of all, improved science, and that has to come from comprehensive studies on experimental basins. So I've shown you a really important study from Saudi Arabia in the 1980s. The sad thing about that study was that the basins were stopped at the end of the 5-year period. We really need detailed monitoring at an intensive level, operating for years and decades. And as I said, the only basin that's done that for arid areas is a small basin in Arizona, Walnut Gulch. Second point is good quality data is really difficult in these harsh environments, and particularly flow data. Flow measurements are quite difficult. I showed you the picture of the flow gauge that was originally washed away and then reconstructed. We need to develop expertise at a local level and a regional level to understand the science and develop and apply appropriate models. And I think there's a huge role to share information within and between the world's arid regions. And I was one of a number of people who developed a program for UNESCO called Wadi, which focuses on the world's arid regions. And that's done quite a lot of work to bring people together and share knowledge and information. And I'll finish with showing you a couple of books that have come out of that program. Now, it's a long time since I was working in Saudi Arabia in the 1980s. And the last decade, I've been working in Canada as a Canada Excellence Research Chair. And I've now retired from Canada, but my last major initiative was to bring the Canadian research community together to address their hydrological challenges, which are really all about cold regions, cold processes, frozen soils, snow, ice, retreating glaciers, and so on. So there were 4 universities that led this program and another 14 universities involved. So we had 18 universities, and we had a grant of about 80 million Canadian dollars. And with supporting money, we had a program that was originally about $140 million. It's now grown considerably with additional inputs from government agencies and industry, as well as the universities themselves. And this has brought people together to address problems that are particular to cold regions in Canada and elsewhere. And at its heart is a set of large-scale observatories, so we can monitor and understand the scientific processes and then apply that knowledge to modeling. So there's a very strong argument that I'm making that we really need an initiative that's big scale and ambitious to take our hydrological understanding forward for areas of the Middle East and other related arid and semi-arid regions. So just to close, if you're interested, there are two books that came out of the UNESCO program, one on hydrological modeling and one on groundwater modeling, but you'll see they're both more than a decade old now, and that work really needs to be updated. And you can check out the GWADI website, which has further information. And then there's a list of papers to some of the work that I've been doing in semi-arid areas, which really led to the award of the Prince Sultan bin Abdulaziz Prize. So thank you all very much for your attention. It's a great pleasure and privilege to contribute to this meeting, and I hope you found this short talk of some interest. Thank you.
Abdulaziz.
Hello, my name's Jim Hall, and it's a great pleasure to be at this conference, albeit online on video. And I'm presenting this work along with my co-author and indeed co-prize winner in the Sultan bin Abdulaziz International Prize for Water, Dr. Eduardo Borromeo. And I'm a professor in the University of Oxford. Dr. Borromeo is with the World Bank and also associated with my group in the University of Oxford. And the work I'm going to describe, which was actually led by Dr. Borromeo, is on the multi-dimensional challenges of water security in the Arab world. The Arab world is rightly regarded as one of the most water scarce regions on the planet compared to the population and the demand for water. But the work which we've been doing has been making the point that the challenges of water security in the Arab world are not just to do with water scarcity, and indeed describing them in terms of water scarcity may not be completely constructive, because there's so much difference between the different countries within the Arab world and the types of challenges that they face and their current status with respect to water security. And in this talk, we're going to try and unpack some of those questions. We're going to look at how climate change adds to those water security risks, how climate change is a risk multiplier. and look at some of the ways in which we might think of responding to those water security risks, many of which are already well developed in some and sometimes all countries within the Arab world, but some of which show more potential from the future compared to the current level of uptake. So first of all, looking at these multiple challenges, as we've already said, the Middle East and North Africa is one of the most water scarce regions in the world. 61% of the population is exposed to high or very high levels of water stress, and 71% of the GDP is exposed. And these are very big numbers compared to other regions of the world. And because of that, we see unsustainable uses of fresh water, especially groundwater. So rates of groundwater depletion, which we can monitor these days with satellite data, are dramatic in parts of the Arab world. In terms of environmental impacts, which I'll talk in a moment, but the draining of wetlands, as we've seen in the lower part of the Euphrates and Tigris basins, has been large-scale changes to the aquatic landscape, which has led to increases in aridity, and also issues associated with displaced persons who were previously dependent upon those aquatic environments, which has led potentially to questions of conflict for those displaced persons. There's also an issue of water pollution. So the amount of water which is being treated before it's discharged into freshwater bodies and into the sea is an issue across many of the countries in the region. And so, for example, if we look at the Gaza Strip here, we know that there are major issues with discharges and runoff of nitrates from agriculture, contamination of groundwater, and the risk of eutrophication of the coastal waters. Desalination, as we will see a bit more in a moment, has become a major source of fresh water, in particular in the Gulf, as shown here. And actually, the use of desalination has reached such a scale that this is having a significant impact on the salinity of the Gulf, and reaching a point where actually desalination becomes less efficient, where the intake water is of higher salinity. And this is becoming an issue, certainly within the Gulf, as well as those brine discharges having an impact on biodiversity in the Gulf. Meanwhile, though we're talking about a water scarce place, there are threats from occasional intense downpours, flash floods, which of course have been a characteristic of the region forever. The landscape and wadis of the desert are shaped by occasional flash floods, but now with human development exposed to those flash floods, they are becoming increasingly harmful hazard for the human populations. And as I've mentioned previously, both in connection with wetlands and in connection with water quality and saline discharges, there are major threats to biodiversity in the region. These are ecosystems which are in some senses, extraordinarily well adapted to their arid environment, but on the other hand, are quite fragile and vulnerable to changes in water availability and water quality. And that is seen in terms of the numbers of species which are impacted, and in particular the number of threatened species which are impacted by changes in the aquatic environment. And whilst water is a scarce resource in the region, it's not being used particularly productively. So here we're looking at water productivity, the number of US dollars of added value, which are gained from a cubic meter of water. And we see that in some countries in the region, the productivity of water is extremely low. So there's scarce water, but that water is not actually being used in a very productive way in many instances. And for the most part, that is because of water being allocated to agriculture, in which the agricultural productivity is not particularly harmed. So this raises the question of whether water is being used in the most productive way in the region. The big picture here then is that if we look at sustainable and unsustainable water uses, the red is sustainable, the red is unsustainable, the blue is sustainable, and then on top of that, we put unconventional use of water, reuse, desalination. We can see a very varied picture right the way across the countries of the Arab world. Some much more sustainable than others, some dependent upon surface and groundwater sources, some much more dependent upon desalination and wastewater reuse. So this is a very complex and very varied part of the world we're talking about. And in terms of access to water services, so drinking water sources, which is what's shown here, again, we see a very varied picture across the region. Ideally, where we want to get to is 100% access to improved drinking water sources. And some of the countries in the region are at that level, but other countries are at much lower levels of access to drinking water, and indeed access to improved sanitation, which is also so important for public health and human well-being. And economic modeling has shown how water insecurity, inadequate water supply and sanitation is really hitting those countries where those essential water services are not well developed, and in particular in the conflict affected countries of the region. Part of the story around these inadequate water services is because the water utilities are not investing enough, both in terms of new infrastructure and in terms of proper operation and maintenance of that infrastructure in order to provide high quality services. And the reason for that, in part, is because the full costs of those water services are not being recovered from the people who are served. In order to sustainably run a water utility, there needs to be enough income in order to pay for the services that are provided. And in many places, within the region, the cost of water is just far too low to pay for a viable water utility. So, on top of all of these multiple dimensions and complexities, we have the growing threat of climate change. And climate change is a threat multiplier here. It's adding to the water stress of surface and groundwater sources. So it's pushing that stress level up because there will be higher temperatures, which is driving up evaporation. And regional climate model studies show that we're expecting reductions in precipitation in the region as well. And that means that we're expecting water scarcity to have a growing impact on GDP. But that could be, to some extent, alleviated and in particular, this proves to be the case in other parts of the world, if one's able to reallocate water to higher value usage, so to use water more efficiently. However, in the Arab world, in the MENA region, that will not be sufficient. And actually, more radical interventions seem to be needed in order to combat water scarcity. The risk is high. This picture here shows how the Middle East and North Africa is one of the areas where droughts are most likely, these are predictions from climate models, to increase into the future. And then in addition to that, we know there will be sea level rise associated with climate change, and that is going to impact the deltas in the Mediterranean, in the Red Sea, and in the Gulf. And here we're looking at the Nile Delta, 50 centimeters of sea level rise, which is what we're expecting by the end of this century, maybe more. 10% of the Nile Delta could be permanently submerged and 4 million people affected. And this is on top of the ongoing process of erosion of the Nile Delta because of the reduced supply of sediment from upstream in the Nile. So the final question is, well, how can we to respond to these risks of water insecurity and climate change? And it's already recognized that wastewater recycling is one of the greatest opportunities within the region. 82% of the water in the region is not recycled, and it could be. This is clearly a much more sustainable solution than desalination, because we don't have the issues of brine discharges and increasing salinity that we saw in the Gulf in the previous slide. And so where we need to be heading towards is a closed loop, a circular water economy, where we're reusing wastewater, extracting resources also from sewage, and extracting energy, which closes the energy loop, whilst at the same time ensuring that there is sufficient water remaining in surface and groundwater bodies to sustain the aquatic environment. That sustaining the aquatic environment is incredibly important to build resilience for ecosystems. And so there's a potential side effect here from very extensive wastewater recovery without putting enough water back into the environment. Meanwhile, resources, nutrients, energy, in particular from sewage, provide opportunities for fertilizers and energy from biogas. Within the urban environment, we've referred to those occasional shocks from extreme rainfall, and so creating green space in the urban environment, which is able to deal with surface water flooding, expanding wetlands, giving room to rivers, is a big opportunity. And the other opportunity out there is the rapidly increasing amount of data for hydrological forecasting and warning, and this is particularly significant in relation to droughts, where using satellite data we can monitor droughts in real time and combine that with forecasting models in order to inform management plans, for example, in relation to water allocation and agricultural decision-making at the farm level. That was a very high-speed tour through a very complex part of the world. But what I've tried to illustrate is that water security is much more than dealing with just water scarcity. The Middle East and North Africa is water scarce, but what I've shown is that the story is very complex. There's a lot of variability between the countries of the region. Some of that comes down to governance, the strength of water utilities, the relative emphasis on agriculture, the degree of technological update, for example, in relation to wastewater reuse. And though this is an incredibly challenging part of the world, and conflict layers on top of those challenges and challenges water governance in particular, there are potential responses which mean that water can be used more sustainably and water security can be built up within the region through a combination of technological interventions, policy reforms, institutional arrangements, which will strengthen water security within the region. And much of what I've just talked about here is written up in this paper in Earth's Future, led by Eduardo Borromeo, with a number of colleagues from the region and from the International Water Management Institute, IMI, who I should acknowledge as well. So it's been a great pleasure talking to you. I wish you an extremely successful conference and look forward to future collaborations.
Good morning. Thank you for this invite to this conference, international conference in Saudi Arabia. I will be talking about our research at King Saud University on microplastic pollution in mixed surface and treated waters in Saudi Arabia, as well as the importance of organic contaminants and absorbed by the microplastics. Saudi Arabia, it's you are from this country, most of the audience, is a problem of water. There is a problem of water. Many of the water is treated water from wastewater. So this water is used after treatment. Mainly the Riyadh wastewater treatment plant delivers a lot of water, which is highly treated, and that goes to different applications or different purpose, like artificial recharge of aquifers, to maintain the ecological flow, and also to create recreational areas, for instance, in the oases and other areas. So you know very well, and all the country now, what I have seen in the last 10 years is much more irrigation surface has increased in the whole country, so you have much more water around. So basically, the problem here that I want to discuss is the microplastics. We started, I think, the first papers in Saudi Arabia about microplastics are our common work with this King Saud University. And we have students there working also in this topic. So basically, microplastics is a big problem, as you know. Approximately, we are talking about a production of 150 million tons per year. Everybody is using plastic. Now, with the COVID pandemic, even the situation is much worse. So the amount of plastics around the world has increased dramatically, and we expect a big increase in the end of the year and the next coming year. So basically, we are talking here now that only in China, the medical waste because of COVID has estimated to be 3 million tons only in 2020. Usually it was around 2.2 million tons. So the increase is incredible. And this is around the world the same thing. So because mask and everything. So the data that I will be showing here is data before COVID, of course. This was collected samples in the years 2019, 2018. Last year, I was also able to be in Saudi Arabia to collect some samples before the pandemic, but you will see that the situation. So basically, what we have here is microplastics and persistent organic pollutants. Microplastics can also absorb many of the chemicals, and we know that the plastic is has a Trojan effect and can absorb different types of chemicals. So the situation with the microplastics and the chemicals is also important. That will be my second part of the lecture. So basically, here we are looking at the waters in two main cities in Riyadh and Al Khubai. Riyadh is the capital, as you know. It's the very well. It's the most populated city in Saudi Arabia, and we look at the channels and the canals and the water in around Riyadh, and especially in South Riyadh, where the wastewater treatment plant is directed, the wastewater treated, and the other city is Al Khubail, one of the most important, or maybe the most important industrial city in Saudi Arabia. And in the east side, as you know, and in this area we also look at the different canals and also make a comparison between the two areas. So I think this may be interesting for all of you, because many of the people here the country, of course, is your country. Many people in the audience is from Saudi Arabia. So you will see that these are different spots, different locations. We look at different types of canals and different. We did a lot of sampling in these areas, looking at different spots and trying to be as much representative as possible. Here is one of the colleagues, Mohamed Sheikh, in collecting the microplastics. You need this type of nets around 20. We pass around 20 liters of water through a Teflon tube nets, and then we collect the samples and we bring all the samples to Spain, where we measure in this case with FTIR. With FTIR, we can identify the microplastics. If you want to have more details, you can ask my colleagues at the King Saud. They have all the protocols, and we do a lot of work together, and we publish quite a lot. These are the typical microplastics in shape, size. You know what is the morphology situation. Here is a different situation of the morphologies of the different microplastics collected in the different spots, different sizes. Also, you can see there is a big diversity on the microplastics. Also, the color, which can be related to metals, to be related to different types of washing procedures, clothing. You know, there's a lot of fibers as well in the water, and also as one of the microplastics formation. So there is a lot of different aspects and size. And here the composition, well, you need a FTIR, and you can see in this particular case is a polypropylene, polyethylene, polyestyrene. They are very common microplastics found, PET, PET, so the polyethylene terphthalate. So these are the four most common the symbols that you find here: PP, PE, and PS and PET. So polyestyrene, polyethylene, polypropylene, and PET are the most common ones detected not only in Saudi Arabia, in most of the world. So this is the comparison between the quantities in between Riyadh and Al Khubai. Obviously, Riyadh has much more population, so you expect 10 times more microplastics than in Al Khubai, and this is what we detected. And here, then what we look here is to try to establish a kind of risk assessment. Well, this is a quite complication how to explain in a short time. Basically we took some calculations using standard methods of mutagenicity and toxicity, and look at the different standards and the monomer composition and all these kind of things and the levels. So basically, to be much more clear, basically means that below 1,000 is no risk or very low, moderate risk. Above 1,000, the risk can be higher. So this is just a question. Here you can see that the numbers are below 1,000. So we are at category 3, which can be toxic but non-mutagenic or much more. Can affect a bit the biodiversity. This is the outcome of the data from basically on the microplastic detection. And here is in the Al Jubail here the two spots, the Al Jubail and the Riyadh. So from the comparison between the two spots, the levels of Riyadh are the most important ones, and they are the only ones that can. These are the risk calculation. I do not go into the detail because we don't have the time for this. But here are how we make all the spots where we measure the microplastics and how we estimate the risk according to the monomer composition and the standards and calculations made according to well-established methodologies. And what we can say here as a first conclusion that all waters contain microplastics. That's one important issue. The range goes between 0.1 to 1 millimeter. The most important polymers by FTIR were polypropylene, polyethylene were the dominant ones. This study can also be used as a reference to better understand the impact of microplastics in artificial surface waters. And from the two spots, Riyadh is the one that can have a moderate, we'll call it moderate risk, and may affect biodiversity, but this is something that we need to look at long term. And utilizing these mathematical approaches, you can really estimate the ecological risk. Basically, it's ecological risk that can affect biodiversity, the plants, or the ecosystem, let's say, mainly in the area of Riyadh, not in Al Jubail. So, but of course, this study was done before the pandemic. We will do it again after pandemic, as soon as I can travel and my colleagues can collect samples. They already started. So I'm afraid that after next year, in a couple of years, the data will be worse because the situation with the plastics has really got worse. Because we have all the masks, all the medical PPE equipment. So I think this is very important to repeat this study, because this data is now a very good an estimation what we had before the pandemic. As I told you, after the pandemic, all the microplastics in the aquatic environment will be much more, at least 20–30% more than these levels. This is what we are expecting, and is around the world. So the second point is what happens with the organic chemicals in these microplastics. We look at the water and sediment samples, and we also wanted to look what kind of chemicals were there. Basically, we look at the polycyclic aromatic hydrocarbons and perfluorinated substances, which are very important. You know, this is Teflon derivatives, and we wanted to know if they are there or not. So we took the microplastics, we are extracted. This is the protocols. I don't want to go into the detail. This is some work that we are preparing the writing. We are writing this publication because it's not yet ready, but we develop it with the same microplastics that we collected. We look at all the chemicals that are present there, the pHs, which are in all the legislation, and then the PFAS. PFAS is now a very important topic because the perfluorinated chemicals are now in the list, in the priority list, on all the countries. There is a big concern in Europe and the US, especially for drinking water, because they are present. They are also estrogenic. They could be estrogenic, so they have quite a lot of effects. Basically, they were pretty much used as Teflon, for instance, in cooking pans. It was very common, and also Gore-Tex. A lot of material contains Teflon derivatives, and now has been replaced. So basically, what we have here is what is the concentration of pHs in different matrices, and what we know is that the different colors, the microplastics is the gray color, so you can see that is microplastic present in water, sediment, in PAHs present in microplastics, in sediment and in water. In sediment is the gray color, so you can see that most of the microplastics most of the pHs, they go to the microplastics. So microplastics has a high absorption capacity. So it means that when we have microplastics, we also have pollutants inside. The PFAS, the same thing. So we also got microplastics color is the dominant one as compared to water and sediment. So what we see here is that microplastics are the main matrix that will absorb all these chemicals and will remain in the microplastic. So it means that the microplastic is not only microplastic itself, the monomers, the polyethylene or polypropylene, but it also contains other chemicals. If we compare then pHs and perfluorinated chemicals, pHs are the blue color and the brown color is perfluorinated, we can see that pHs are certainly dominant in the microplastics. So pHs have a high absorption capacity in the microplastics. So, and pHs, as you know, some of them are carcinogenic, benzoypyrene, sorry. They are well known as combustion process, you know, in the combustion, in the car industry, in the oil industry. I'm sorry to tell you because you have a lot of oil production, but pHs are formed during combustion of fossil fuels. So they will be absorbed in the microplastics, and of course then microplastics will contain these chemicals which are toxic. So then we did some experiments in the lab to see. This is ending my presentation because I think I have still 5 minutes. So we did some experiments in the lab to understand a bit the absorption. This is more theoretical calculations and also lab experiments to see make some exposure with the mixing the microplastics. In this case, we use polyethylene because polyethylene is the dominant microplastic present. So we use polyethylene, and then we use different chemicals to understand better the absorption capacity of this. Polyethylene, as I told you, polyethylene and polypropylene are the most abundant ones. So we use one pure standard to understand the absorption of chemicals. And then here you can see the absorption capacity according to the days, different days with the equilibrium time, 15 days, more days or several weeks, depending 28 days up to 28 up to 1 month, you can have certain equilibrium of this. You calculate also the log KOW, octanol water partition coefficient, so you know that these chemicals they really absorb into the plastic. After 20 days, the equilibrium is constant basically, so you get these chemicals perfectly absorbed into the microplastic, and then they will be stable and they will remain there for quite a while. So I think, and that's one of the problems that we have. Of course, if there is a plant and the plant there is we know that there is a plant uptake. This is another research line that we performed here in Saudi Arabia. We did quite a lot of studies on the plant uptake of microplastics and also mainly organic pollutants, but now also microplastics. Then we know that the plant uptake will contain microplastics and the pollutants. So this is also that what can happen at long term, that the biodiversity, you have a very good, excellent biodiversity in Saudi Arabia. I think that they may affect at long term the biodiversity. This is something that we will study with my colleagues at the King Saud University, Professor Ahmed Al-Farhan and Mohammed Al-Sheikh. So, and the students, we will work on this because I think they are specialists on botany and they know pretty well on this. So to better understand the models or what is going on in the absorption capacity, we did use different models, Henry model, French model, and Langmuir model. Basically, the best model that was adjusted to the source to understand better the absorption capacity of these chemicals was the French model. So trying to a linear model, adjusting this to the linear model, and that we could understand a bit well what is the concentration. You can see the graphs here are pretty good. So going to the end, because I have only 3 minutes as far as I know, the more relevant association terms we're using to understand a bit the problem. We know that pH absorbing are more sorbent into the microplastic than PFAS, than perfluorinated chemicals. The linear methods can explain, the linear models can explain the absorption. So there is a linearity. After 20 days, the absorption is very important, is stable. The studies performed at the laboratory understand we can control the situation. We know how it works now, and we also know that there are also dependence on the microplastics type and size. You know, microplastic is being degraded in the environment, and basically the size is going down. So microplastics can also go at certain moment to nanoplastics. We did not investigate, by the way, nanoplastics. Nanoplastics, you need to look is a nano level. We did not look at so low level because you need more tools, you need more time, and it's much more time consuming. But we know that microplastics they will degrade. And of course, the pHs or the contaminants will also go with the microplastics or nanoplastic. In this study, we also, I did not show it because it was much longer than the time for the presentation. We did study different variables like salt concentration, pHs, and we know that the small variation of these parameters can affect also the absorption capacity. You know, in Saudi Arabia, you have specific conditions because, you know, it's a lot of, the temperature is a very important one because you have always high temperatures and the water is affected at high temperatures. Also the pH can be a condition, and salt concentration. So all these absorption capacities and the behavior of these chemicals can be changed according to this to the different natural or environmental concentrations. Just going to my last one, and I think it's almost 20 minutes. Microplastics were isolated in these two places, and I think that gives us now the first idea what is going on in surface water, treated wastewater, surface waters in these two important places of Saudi Arabia with the waters around. I think this will be very good because this is like a baseline study, first study, and we continue in the future. The next ones will show the impact of the COVID and other impacts if really the country is using much more microplastics or not. We will be able to monitor in the future if the increase of plastics is going up or going down. No? Probably now will be up because we have this pandemic situation still. It's very important to understand that microplastics is not only microplastics and the monomers inside the microplastics, but also the contaminants which are sorbent there. And microplastics were mainly, we're talking here pHs and PFAS, which are very ubiquitous pollutants. They are everywhere, and you can find in all the waters around the world. So I think they are also now part of the microplastics. Results show that the absorption of this fluantene, antrazene, and PFOS and PFO are the most important perfluorinated. They are in the legislation, these two chemicals, because of the toxicity. They were also studied in the microplastic and sorbent. So basically, we have these chemicals are there, and they are in the microplastics. And I think it's important to understand that all this research will help to better understand also the microplastics in areas like Saudi Arabia, where the climatic conditions is very different than other areas. Is an extreme climate condition, and in Spain we have Mediterranean, but here you have even much more extreme conditions. The temperature is really going up most of the time of the year, and you have a lot of sun hours as compared to other countries. So it's an extreme conditions, and I think this will also give us an overview of the whole situation on this big problem, big issue, because many people say that microplastic will be the next pandemic that we will need to face and we'll need to cope and we need to solve in the future in not only in Saudi Arabia, but also the whole world. I mean, it's a real problem everywhere. So I think it's something that if we know much better the situation, we will better can solve. I mean, one way to solve is, of course, one way is to produce better plastics with more degradable, and the second one is also to make an upgrade of treatment plants. These are two solutions for the future. Thank you very much for your attention.
Good afternoon, ladies and gentlemen. Welcome to my presentation on changes in flood risk. My name is Zbigniew Kundzewicz. I'm a member of Academia Europea and a corresponding member of Polish Academy of Sciences from Poznań, Poland. And I am a recipient of a Prince Sultan bin Abdulaziz International Prize for Water, the Surface Water Prize 2020. My talk consists of 4 parts: introduction, observations, projections, and concluding remarks. I start introduction from a slide demonstrating that in fact, flood risk is a complex idea, and its components are flood hazard, exposure to floods, and vulnerability to floods. That in turn depend on the climate system, terrestrial and hydrological system, as well as socio-economic system. Why has the flood risk grown? Well, some people say they haven't really grown. It's a CNN effect. So it's a media effect. But this is not true. The flood risk has grown due to several changes in climate, like enhanced intense precipitation, land use change, urbanization, deforestation, and also changes in socio-economic system, that is increasing exposure, floodplain development, and growing wealth in flood-prone areas. In the old days, at least in a moderate climate of Poland, a 1,000-year flood in a river did not do any harm, because there were shrubs and trees growing along the river. Now, they are buildings. Of course, we have dikes, but dikes do not protect us from a 1,000-year flood. Moreover, the new 1,000-year flood is higher than the old 1,000-year flood. Why? Well, even if we assume that the climate and the precipitation is more or less the same, we have more urban areas, and hydrograph in an urban area has a fast and high maximum, whereas a rural area has a slower and lower maximum of runoff for the same precipitation falling on both urban and rural area. But assuming that the precipitation does not change would be false. There is more room for water vapor in a warmer atmosphere. So if the temperature grows, then the saturation vapor pressure also grows. And this means that the risk of intense precipitation is increasing. There is a higher potential for intense precipitation. Observations, the other part of my talk. Many floods with high material damage and fatalities have been recorded worldwide. And you see there have been many floods in the Arabian Peninsula. Arid environment of Saudi Arabia is not immune to occasional floods. Some areas of Saudi Arabia are regularly threatened by seasonal flash floods, despite low amounts of annual precipitation totals. For instance, the city of Jeddah in Mecca province suffered major flooding in November 2009, with many fatalities. There is a lot of information about Saudi Arabia floods in a flood list portal, where you can find also photographs. Now, illustration coming from Central Europe, from Dresden in Germany. There have been many floods there since Middle Ages. The first column that you see to the left represents an event of summer 1275. But recently, well, relatively recently, in 2002, we had the highest river level ever observed. It was after a summer intense precipitation. But one cannot say that this is a kind of a regular time series. For instance, during the 20th century, there was no high dramatic floods. The two small floods are much smaller than the record. And before that, since the year 1520 until 1870, floods happened in winter, which means they were caused by ice jam, something very exotic to you, to Saudi Arabia. But it happened during European winters many times. Ice jam and snow melt, winter floods, when the rivers were frozen. I made a study together with colleagues on flood risk in Europe, and we noted that the number of large floods in Europe has been increasing. However, it's not a regular increase. There is a strong interannual variability. In some years, the number of large floods was very high, like 2010, and in some years, like 2011, very low. So it was a difference between one event in 2011 and 17 or 12 events in 2010, depending what you count, whether severity is important or magnitude. This is a cover of my book published in England on changes in flood risk in Europe, with many European countries considered. And this is an illustration from the book I edited. A relatively small country, Germany, much smaller than Saudi Arabia, has a very complex map of trends in intense precipitation. So it all depends whether you deal with annual data or warm season or cold season. And the signal in increasing intense precipitation is strong in a cold season, especially over the diagonal from northeast to southwest of Germany. For warm seasons, the situation is much more complex. And for annual, yes, there is the same diagonal with trend, but much weaker than for the cold season. What is also important is that mean duration of circulation patterns for the winter season has been changing. WZ means west cyclonic, and this is a kind of a floody circulation pattern on the rise in a more recent decades. I would like to refer to a paper that we published in a water journal about climate variability and floods. We review the whole globe. There is nothing in the Arabian Peninsula that we could find in the literature, but there are some studies around the Arabian Peninsula. Blue color means that there is a regional predisposition to abundance of water in the Horn of Africa, Ethiopia, during the La Nina phase of ENSO. In contrast, red dot and red space means that there is a regional predisposition to floods and intense precipitation during El Nino, a warm phase of ENSO. And also to the north from Arabian Peninsula, there is a link between a negative NAO, North Atlantic Oscillation, negative phase of NAO, and abundance of water. Another paper that I led was published in Earth Science Reviews and refers to climate variability and floods in China. During a strong El Nino phase, typically there are high annual precipitation sums over the whole of China. But if you go in details and look at the links between El Nino and La Nina and abundance of water in river basins in China, the situation is quite complex. However, El Nino and La Nina do have a link with abundance of water in the large country of China, and it's all 10 large river basins. Sometimes links between ENSO and intense precipitation or high river flow has no time lag. That is, in the same year, there is a high river flow and, for instance, strong El Nino. But sometimes there is a lag of 1 year. It was perhaps quite interesting and maybe even a little surprising that we also found a link between PDO and summer precipitation total in China. PDO stands for Pacific Decadal Oscillation. This illustration comes from an old paper that I published together with a Japanese colleague, Kuniyoshi Takeuchi. On the x-axis, there is a gross national product per caput. And on the y-axis, we divided the material losses by the number of fatalities. So in the left bottom corner of this diagram, we have $20,000 per fatality observed in Bangladesh during their large coastal flood. And in contrast, right top corner, it is $400 million per fatality in the United States Midwest flood 1993. So compare 20,000, 400 million. In the United States during the Midwest floods, there were 40 fatalities only and $16 billion losses. So if we divide, it is 400 million. Exposure to floods differs dramatically between countries. In these two panels, I show exposure measured by the number of people exposed to the left. X-axis is an absolute value and y-axis is a relative value, percentage of national population. Big GD stands for Bangladesh, that has over 10% of national population exposed to floods, and over 10 million inhabitants, well over 10 million, because this is a logarithmic scale. Bangladesh, Cambodia, and Vietnam are the three most vulnerable countries. To the right, there is a exposure of total assets and GDP. On the x-axis, absolute, on the y-axis, relative, proportion. Again, the same countries, Bangladesh, Cambodia, and Vietnam. So USA is most exposed as far as the sum of total assets is concerned, but this is only a small proportion of national GDP because United States are a very rich country. Projections now. 13 years ago, I was honored to publish a paper together with excellent scientists in Science journal, Science magazine. Stationarity is that, weather water management. We showed the following map that could be summarized as follows. The areas that are wet are likely to be even wetter in a future climate, whereas the areas that are dry are likely to be even drier. This is a belt around the Mediterranean Sea. The Arabian Peninsula and Sahara, so really dry places, are not touched here because the models do not agree as to the direction of change. So if there is a white area, the models do not agree. The color means that at least 8 of 12 models agree on a direction of change, and hatching means good agreement of 11 or 12 models. Projections of intense precipitation show you a very clear picture. Western Asia with the Arabian Peninsula show you a horizontal line at the level of 20. This is the level of 20-year daily precipitation, sun. And we can see that in the future, both near future and remote future, what used to be a 20-year precipitation is likely to be much more common. Perhaps 15-year or 12-year, or even 10-year precipitation for the more remote horizon, and for less advantageous greenhouse gas emission scenario. Now, global study of Rutger Dankers, published in PNAS, Proceedings of National Academy of Sciences. Q30 increase and Q30 decrease are shown in top panels. In Arabic Peninsula, the signal is not very strong. So some models show you Q30 increase, some show Q30 decrease, but more show Q30 increase, which means increasing risk of the floods. Another global study by Giuntoli, including Arabian Peninsula, where also increases in frequency of days under high flow conditions are dominating. This is based on the multimodal ensemble and a very disadvantageous scenario of RCP 8.5. 5 GCMs and 5 global hydrological models have been used in this study. And in this paper that is available in public domain, we explain differences in flood hazard projections in Europe. So there are many studies. There have been many studies on flood hazard projections in Europe, but the writers do not agree on the conclusions. It all depends on the model, on the approach. We discuss the reasons of differences and interpret their causes. And now the final 2 technical slides of my talk, concluding remarks. The impact of climate forcing on flood risk is complex and depends on the flood generation mechanism. Some flood generation mechanisms that I covered in my talk are not relevant in Saudi Arabia and in the Arabian Peninsula, because you do not have frozen rivers in winter. You do not have rivers at all, and you do not have snow cover that could lead to snowmelt floods. However, the second bullet is also relevant for you. Higher and more intense precipitation has already been observed in many areas, and this trend is expected to strengthen in the warmer world, directly impacting on flood risk. However, it is really difficult to disentangle the climatic change component from strong natural variability and direct human impacts. Common sense changes to design rules have been introduced in some countries based on precautionary principle rather than robust science. So robust science does not give you a hint. You need precautionary principle and possibly common sense changes, like in a future climate at the horizon of 2080, 100-year runoff could increase by 20% or 15%. So they are design rules like that in several countries. So we have to be careful with flat rate statements, because they are caveats. They are conditions that have to be specified, that have to be interpreted. And my last bullet at this concluding slide is that since it is naive to expect availability of trustworthy quantitative projections of future flood hazard, In order to reduce flood risk, one should focus attention on identification of risk and vulnerability hotspots and improve the situation in areas where such hotspots occur. There's no way to have rigorous quantitative projections of future flood hazards. Now I'd like to acknowledge the project, Interpretation of Change in Flood-Related Indices Based on Climate Variability, funded by the National Science Center, that supported my work over the last 2.5 years. Thank you for attention.
Morning, I'm Jay Lund from the University of California, Davis. I'm here to talk a little bit about hydroeconomic modeling and its use for making progress with water management in a difficult world. As usual, the real work behind this presentation, behind all of this work, is done by quite a few graduate students and colleagues over the course of a decade or more. So I thought I should acknowledge them and have a nice picture of them in a more relaxed time. The main ideas I want to get across today are some of the things that you already know. First is that water problems are complex, messy, and involve multiple objectives. But among the many objectives for managing water, economic objectives tend to be pivotal. That doesn't mean they're always the most important, but they tend to be the objectives that make solutions go one way or the other, and make judgments go one way or the other. Presentation today is about hydroeconomic models. And these models are computer models of integrated water systems that integrate the hydrologic, infrastructure, and economic aspects of water systems and those relative decisions. This is mostly how real water systems work, where we have to integrate these different disciplines together to make a functioning water system that provides for the needs of the society. These hydroeconomic models organize, analyze, and help us find better water decision portfolios, because we're not managing only water supplies, we're usually also managing water demands and the infrastructure that's between the supplies and the demands. So we want to look at these as an integrated system and organize them as an integrated system. Hydroeconomic models also provide a framework for understanding the multi-objective trade-offs, the uncertainties, and possible adaptations of this system to different uncertainties as they unfold into the future. Overall, these kind of models, to me, the real major intent of them is to help us organize problems so that we can better discuss them and their solutions with the wide variety of authorities and stakeholders that are involved in most water system management problems. Next, let's talk a little bit about what a hydroeconomic model is. Hydroeconomic model has several different components, and so to the right here is sort of a schematic of what a simple hydroeconomic model consists of. It consists of water sources, both surface water and groundwater, aquifers. It has water demands, hydropower, agriculture, urban uses scattered throughout the region. It has infrastructure of reservoirs, aqueducts, treatment plants, pumps, and hydropower systems that we operate in order to get water from the supplies to the demands at the right place and the right time with the right kind of reliability. And then we have economic performance. So for each of the water uses, we have not only a target for delivery, a volumetric target for delivery, but we also have, in a hydroeconomic model, how much is that water worth? The first units of water are usually worth more than the last units of water that we deliver, because the first units of water you use for the most valuable uses. And so we replace sort of targets, single point scalars of what a what the water demand is with a demand curve, sort of from microeconomics. And so this allows us, these water demand curves give us a way of quantifying the costs of water scarcity. Certainly in semi-arid regions such as California, we will always have some water scarcity. And so we're very interested in, well, what is the cost of that water scarcity? And how can we operate to minimize those costs? Plus, we also have operating costs we're trying to minimize. So typically, from a regional economic perspective, we want to minimize the sum of water scarcity costs and operating costs. In most modern water systems, we also tend to have some environmental flows that we're trying to maintain. So here in this diagram at the bottom, we have some environmental flows that we would like to maintain at the bottom of the system. Those might be represented with costs as well, but it's more likely that we will represent them as a very firm constraint that we will try not to violate. In managing this system, we have a wide range of decisions. We have water demand decisions, water conservation decisions at the demand side. We have water operations decisions, how much water to store in reservoirs or aquifers, how much water to divert and allocate among the different uses, how much to pump versus how much to release, how much to store. And so the hydroeconomic model really helps us explore the portfolio, the very wide portfolio quite often, of water management actions. So we often have thousands of different decisions that we're trying to coordinate with these models. Again, coming back to the objectives of hydroeconomic modeling, we're trying to develop a framework to organize and find better water decision portfolios. These portfolios consist of water supplies, different ways of managing water demands, and different ways of managing infrastructure. So this table down below sort of develops a taxonomy of what a water supply system portfolio might look like. It has quite a variety of water sources, capacities for storage and conveyance, for treatment, different kinds of treatment, all of which involve different expenses and different operations that we can make in terms of storage and conjunctive use and treatment operations. We also have different ways of managing water for the different water demands, different kinds of water conservation, different kinds of water use efficiency. And then because these systems often involve many different individuals and many different decision makers, ranging from the individual decision makers that decide how much water they're going to use on their farm or in their house or in their business. Those are the most numerous decision makers on the demand side. But we also often have several different groups that are responsible for different water sources and different kinds of infrastructure, or different marketing agreements or exchange agreements between different water utilities. So we have quite a few incentives to help people work better together as well. And so what we're trying to do is organize these problems and organize these solutions within an economic framework and an engineering framework, so that the discussions that have to occur between the water users and the water managers are more productive, and the policymakers as well. We have here a model that we've developed over the last 20 years called Calvin. It's a model of California's intertide water supply system. And when we made it back in early 2000s, we wanted to make a model that represented the system as it was really operated. We found that after some recent droughts, that the water managers actually operated both surface water and groundwater together and various types of infrastructure together. And they also simultaneously had to manage the water demands as well. So they have different kinds of long-term and short-term water conservation measures, water demand management measures that they would take for urban water uses, agricultural water uses, hydropower, even sometimes environmental uses. So this turns out to be a very complex system. And to manage it in an integrated way, for us, the easiest way to look at that and the most economically rigorous way to do that was with an optimization model. So we have an economically driven optimization model driven by the economic values of water delivery for agricultural, cities, hydropower, And then we have constraints for environmental flows, environmental uses, and state water policies. This model prescribes monthly system operation over a 72-year period with a representative hydrology, historical hydrology. And to me, the most important thing about this model, and all hydroeconomic models really, is that they force a quantitative understanding of the integrated water and economic system and the decisions that are involved in operating it. So this is a schematic. This is the model schematic for this system. It has quite a few reservoirs. I think we have about 50 surface water reservoirs, about 40 groundwater reservoirs. We have water demands for almost 40 million people, and different elements of infrastructure that are run by thousands of different local and state and federal governments that all have to be coordinated to have a functioning water system. So this is the schematic for the model. This is a detailed schematic of one of the parts of the system. So you can see the reservoirs are the triangles here with inflows coming in around the mountains. We have these dirty triangles here, which are groundwater reservoirs, groundwater aquifers. We have water demands are ovals, so the rusty ovals are urban water uses, each of which has a economic demand function to it, or economic benefit function for water deliveries. The blue ovals are different agricultural regions that get water from surface water, groundwater, or both. And they also have monthly varying value functions for the delivery of water. And then we have lots of different canals, rivers, hydropower plants, pumping stations, all of which have different capacities and costs for their operation. But this is just a small part of the statewide system, but it gives you a sense for the amount of detail that we had to go into, that the many students had to go into in order to quantify this system and interrelate all the many different parts. We were told when we first came up with the statewide schematic, which was the first statewide schematic for all of California's water supply system, that by itself was worth the what the agency paid us for the first project. Let me say a little bit more about the economic value functions for the system. So here we have, for the different months of the year, the economic values of water delivery for one region down in this part of the world. But you can see different parts of California have different marginal values for water delivery. And so the model will be allocating water among them. The model results have time series analyses for lots of different locations, water management decisions, delivery reliabilities, operating costs, as economic results, overall benefits, economic values of additional water, benefits to each user, and the economic values of expanded capacities on all of the bits of infrastructure, and the economic cost to all the other water users of environmental flow requirements. We've done quite a few applications of this model for a lot of different water problems in California, many of which have helped influence discussions about California water and I think even water policies for the state of California regarding capacity expansion, water markets, environmental restoration, climate change, environmental water supplies, groundwater management, and management of some of our more difficult parts of the system, such as the Sacramento-San Joaquin Delta. This slide gives you some ideas of what are some of the economic results that come out of this model that you don't get with normal simulation models. And this is the economic value of expanding different surface water reservoir capacities and different canal capacities, aqueduct capacities for different hydrologies. And you can see the numbers vary quite a bit with climate, and they vary quite a bit by location. This has been a very successful model. We still continue to improve it and adapt it. It's run both at the University of California, Davis and the University of California, Merced, and different versions of this model, and the fundamental ideas of it have been adapted all over the world, from China to England to Spain, all over the place. Some things we're currently working on to improve this model is to make it a little bit more multi-objective. So this is a newer version of the model where it operates with what we call limited foresight. So the classical models, versions of the model would look at the entire 82-year record and optimize it as a deterministic optimization. This newer approach develops economic benefit functions for carryover storage between years, given California's hydrology. And this has provided a lot better, more stochastic optimization of water operations for the system. And so each of these, this is a whole bunch of thousands of model runs that were done to look at the trade-off between economic benefits and ending groundwater overdraft in the state of California. So you can see where we're a very myopic operation that doesn't really care about the future, has quite a lot of overdraft and quite a lot of cost. And if you optimize from that perfectly, without considering overdraft, you end up with this perfect foresight result. If you penalize overdraft, you end up with quite a bit less overdraft and quite a bit better and a bit slightly worse economic performance. If you prohibit all overdraft, you end up with, maybe $500 million a year of additional cost. But in between, there's really an entire trade-off curve with limited foresight, where the loss of perfect foresight going from this point to here really only cost you $150 million a year or so. That's that's a lot, but it's not a whole lot considering we're talking about $5 or $6 billion a year of economic benefits from this water system. So we can see the trade-offs between different amounts of overdraft and different amounts of economic performance. Some of the other things we're looking at is adapting these kind of water management portfolios that come out of these models with climate change and uncertain climate change over time. So as conclusions, again, coming back to the earlier slide, water management problems are complex, messy, and multi-objective. However, economics tends to be the overriding objective for most decisions in the design and construction and operation, daily operation of these systems. Hydroeconomic models integrate the hydrologic, infrastructure, and economic aspects and decisions of these systems, and helps us model a much wider range and integrate a much wider range of management options and management decisions than we could normally. We're trying to organize, analyze, and find better water decision portfolios, combinations of supply, demand, and infrastructure management decisions and sizing decisions that complement each other, that go well together, and serve the purposes of the system. We provide a framework for understanding the multi-objective trade-offs, as we saw in that earlier trade-off curve, including uncertainties and adaptation. And overall, trying to help organize these very complex and difficult problems to have a better, more productive discussions and better solutions. Because I'm a university professor, I will leave you with a few further readings, and I think I will end there. Thank you very much.
I'm Rita Caldwell, Distinguished University Professor at the University of Maryland, College Park, and Johns Hopkins University. I'm delighted to have the opportunity to speak to the 9th International Conference on Water Resources and Arid Environment. The topic of my discussion is climate, oceans, human health, and what cholera can teach us about COVID-19. The main topic of the discussion is water-related diseases, of which cholera, of course, is the most notorious, with about 2 billion cases a year and almost 2 million deaths. Cholera is a global disease. It's a water-related, that is, it's transmitted by water, a diarrheal disease. And interestingly, we're in the 7th pandemic, which started in the 1960s. So we are currently in 2 pandemics, that of cholera and also of COVID-19. Cholera occurs in about 50 countries. It affects about 7 million people globally. And we've unfairly labeled the Bengal Delta as the native homeland of cholera outbreaks. However, 100 years ago, cholera was active in the United States, Canada, Europe, England, and other countries of Asia. The discovery that we made is that cholera bacteria are naturally occurring in the environment. They exist in the aquatic habitat, carrying out important functions of cycling carbon and nitrogen. And we have seen new biotypes emerging. So it's really unlikely that we can eradicate cholera, but we can control it. No question about that. Now, the early work that we did on cholera was in Maryland. This is the Chesapeake Bay on the Atlantic coast of the United States. We started our work back in the 60s and the 70s, and the numbers of the stations where we take water samples even at the present time. The discovery that we made was that the bacterium is naturally occurring in the environment, and you can see the bacterium, a curved rod with a single polar flagellum, a tail, which allows it to be motile, active, swim in water. The bacteria are associated with plankton. That was another discovery, that the plankton, the copepod, the zooplankton, and the copepod is the dominant form, are the carriers or the host, the vector of the cholera bacteria. This is the copepod, and you can see this is a female about to release her eggs into the water column. The surface of the egg sac on the left is coated with the bacteria, which produce a very powerful proteolytic enzyme, which causes the sac to break and release the eggs into the water column. We developed very early, some 25 or 30 years ago, a simple model of the transmission of cholera to humans. First, there is in the spring, when there's plenty of sunlight and the water temperature has become very warm, the plankton, the phytoplankton that carry chlorophyll, become very abundant. And then the zooplankton, the microscopic animals comprising plankton, feeds on the phytoplankton, and the zooplankton become abundant. When they have run out of food, the population crashes and releases the vibrios into the water column. And then if humans will drink the water that has not been treated in any way, the potential of coming down with the disease then takes place. One point I should like to make is that cholera is a dose-dependent disease. It requires about 1 million bacteria per milliliter. Let's just say 1 million bacteria per teaspoon of water, so to speak, in order to cause the complete disease of cholera with vomiting, diarrhea, sodium-potassium imbalance due to dehydration, and the potential of death. Now, we had been criticized from our early work in the Maryland area in the Chesapeake Bay that this might not hold, might not be the same in Bangladesh. So we were challenged, went to Bangladesh, and in the remote villages found that indeed the villagers were collecting water from the ponds without any treatment, bringing it back to their houses for drinking water for the family. Now, what we discovered was that the very same pattern held in Bangladesh, namely that the bacteria are associated with the copepod predominantly, though you can pick the bacteria up in the highly contaminated ponds on other kinds of vegetation or other kinds of animals in the water system. However, it is clear that person-to-person transmission is very significant. Nevertheless, the source of the bacteria is the environment. And so I think this principle is really critical to understand. Now, the fact that a satellite was launched about 1985, some 35 years ago, that measured chlorophyll, sea surface temperature, and sea surface height. This was launched by NASA, the National Aeronautic Space Administration in the United States. It occurred to me that because there was this relationship between phytoplankton carrying chlorophyll, zooplankton feeding on the phytoplankton, and then the breakdown of the zooplankton releasing the vibrios into the water column, that we could use satellites to predict outbreaks of cholera. And in fact, that's what we did. This was published 21 years ago in the Proceedings of the National Academy of Sciences of the US. The red line are the cholera cases in the villages along the Bay of Bengal. The blue line is the water temperature in a 1-mile quadrant just off the coast in the Bay of Bengal, measured by satellite sensors in the Landsat satellite that had been launched in the 1985 era. We were able to get extremely useful results showing a very significant relationship between cholera, chlorophyll, and rainfall. And in fact, we were able for Kolkata as it's now known, that for every milligram per cubic meter increase in chlorophyll, when the sun came out and the phytoplankton bloomed, they would be correlated with about a 33% increase in the number of cholera cases. And if there was a millimeter per day increase in rainfall, that could account for a 7% increase in the number of cholera cases. And in Bangladesh, the very same relationship was determined. So we have a prediction, a crude one in the early stages, but we have developed a more sophisticated model based on doing analyses of data of India records from 1823 to 1923, putting that into the computer and coming up with historic data as well as the modern data, showing that when there's a very warm cycle and 4 weeks later, a very heavy rainfall in an area of the world, in a country where there is poor sanitation and not good access to safe water, the risk of cholera will be very high. We now use much more sophisticated satellite sensors, starting in 1996 with the very early work with Landsat. And currently, we now use a variety of modern satellites launched in the last 4 or 5 years that allow us to monitor movement of populations, as well as the temperature of a body of water that's 1 meter square. So instead of having to measure a mile square water quadrant off the coast of Bengal, we can now measure the chlorophyll, turbidity, and other factors in the ponds directly. Now, we have been able to expand the application to analyses, for example, in this case, a hurricane that traversed Haiti, came up across the east coast of the United States, and was associated with an outbreak of cholera in Haiti. We did a retrospective analysis. We went back to that particular cholera outbreak that followed the Hurricane Matthew in 2015. And with our sophisticated model, you can see on the left our prediction of risk. And the darker the red, the higher the risk. And you can see on the right the actual cases and the geographical location of those cases. So the model has proven extremely successful. We did a similar analysis for Yemen. In 2017, there was a horrendous outbreak of cholera, the worst recorded historically up to that time. And you can see on the left our risk map for cholera. The darker the red, the higher the risk. And you can see in the bottom right the actual cases. Now, this turned out to be of great interest to the British Aid Agency and to UNICEF. In fact, we received a phone call in January of 2018 after we had published our data for Yemen and this analysis in a scientific publication, which was picked up by a colleague in England. The phone call was to ask us if we could collaborate and provide risk maps on a monthly basis for Yemen, and they would locate medical supplies, safe water supplies, and physicians where we indicated the risk was highest. And so we now do real-time prediction for Yemen, for UNICEF, the British Aid Agency, working with the British Meteorological Agency, and of course funded by NASA. And this allows us, now we produce every 2 weeks a month ahead projection of the risk of cholera for Yemen. And this has proven to be extremely beneficial. Let me turn very briefly now to another aspect of our research, and that's doing DNA sequencing to identify characteristics of microorganisms in water systems. What we do is extract DNA, the community DNA from the water, food, sputum, blood, urine, clinical samples, or just water from the environment, any kind of sample. The DNA, once sequenced, the reads from the sequencer are matched up to a database which we have established of 160,000 highly curated bacteria, viruses, fungus, and parasites. This allows identification of everything in the given sample, the bacteria, the viruses, the fungus, and the parasites. We can also, because we have an additional database of the genes coding for antibiotic resistance, pathogenicity properties, and for metabolism. And so we can characterize and identify the microorganisms right down to strain. Strain is very important. If you're a physician, you know that we carry in our gut harmless E. coli. But if we pick up H0157 strain of E. coli, that can make us very ill and even kill us. Similarly, with Lactobacillus casei, one strain is used to make yogurt, another strain is used to make cheese. Now, we've applied this technique to determining water safety. We've been working with the Orange County Water District in California. They have had a drought in California, and they have been reusing wastewater. 50% of the water coming into their drinking water purification plant comes from the sewage plant. The sludge goes out to sea, the wastewater comes into the drinking water plant. We have been working with the Orange County Water District to determine that these steps of treatment are very effective. The Q1, the water coming from the sewage plant, is screened, treated with sodium hypochlorite, subjected to microfiltration, reverse osmosis, UV irradiation, chlorination, and a variety of other techniques. We have been able to show them that, yes, that gray area cloud covers all kinds of bacteria coming in with the wastewater. But once it's gone through microfiltration and reverse osmosis, the only bacteria we can detect the water bacteria, which are common to any water supply after treatment. Similarly, we can show the viruses are removed. In the Q1 water, there are human viruses and even viruses of agricultural interest. For example, a pepper virus that attacks pepper plants, but not humans. And then once it's gone through treatment, the only viruses we pick up are the bacterial viruses, which do not affect humans. And similarly, the concern was about antibiotic resistance. If you mixed sewage bacteria or sewage water with river and groundwater, would you transfer antibiotic resistance coming in with the sewage bacteria to the groundwater bacteria? The answer is no. The only antibiotic resistance genes we picked up were almost predominantly on the aquatic bacteria that had come in with the groundwater or river water. In other words, the naturally occurring bacteria and antibiotic resistance. We've been very interested in drinking water, the metagenomics and microbiomes, and that is, we've taken samples of bottled sparkling water, purchased water from the supermarket, taken water from public fountains, drinking water fountains, and even from an artesian well. And what we have found is that we could differentiate the microbiological population. The green dots are the bottled water from the supermarket. The red star and the triangle are drinking fountain and tap water. And then the blue dot is very interesting. It carries, this is the natural sparkling mineral water from an artesian well. And it was the only sample that had some of the Archaea bacteria, a separate phylum of bacteria. We did not pick up any indicator bacteria because the water was treated well, but there are bacteriophages, and the bacteria are predominantly the kinds of water bacteria you would find in any system and without any pathogens in the drinking water. Now, what has this got to do with COVID-19? COVID-19, of course, is caused by a virus, COVID SARS-2 virus. But we now know, a year after the beginning of the pandemic, that the virus attaches to a receptor. These cells, the ACE2 receptor cells, are found on the lungs, liver, kidneys, intestines, on the heart and blood vessel cells, and also in neural tissue, because we know that some of the extreme cases of COVID-19 lose the sense of smell and the sense of taste. But we tested with our DNA and RNA sequencing method and found very early last year in February, just when the pandemic had been announced, that we could, in fact, detect in stool samples or any other samples the SARS virus and its variants. That led us to take advantage of the information published, in this case by a team showing that about half of the individuals who had come down with COVID shed the virus in their stool. And then we also determined, as shown by this study, that if you read from the top to the bottom, you can see there are 41 patients. And then if you read across, the red line indicates the time period that the throat swab or the nasal swab was positive for that patient. And the orange line indicates the time that the stool sample showed the presence of virus. Please note that for almost half of the patients, they shed the virus weeks after the nasal swab or throat swab was negative for the virus. We have used that to our advantage by working with the state of Maryland to test sewage plants and their outlets in Maryland, as well as analysis of nursing home sewage outlets, dormitories on college campuses. And in the early study, which we started last June 2020, we showed that in this part of Frederick, Maryland, one location, one city in Maryland, that there was a peak where that blue line is the N target genes recommended by CDC. The orange line are additional genes that we have used in our study, as well as the N genes, to confirm detection of the virus. And we were able to show that in July, there was a very big increase in the sewage plant that samples that we tested in Frederick, Maryland. And sure enough, about a week later, cases of COVID-19 were detected in Frederick, Maryland. Now, we have extended this wastewater testing so that we now can quantify the viral load, use it as an early warning signal for outbreaks that may be occurring in the community well before it's even detected or determined by patients or victims of the COVID-19. We're able to do strain typing and both metagenomic and metatranscriptomic analysis to show everything in the sample, as well as the COVID virus and other pathogens. And this, I think, is turning out to be very interesting. In a highly controlled assay testing for the virus, the samples are spiked with a controlled phage to determine accuracy, and that allows us to be able to provide very good analyses using the target gene and the ORF1 receptors as well. And so that gives us the opportunity, as shown here, by doing metagenomics, we're able to show that indeed there are a dominance of other kinds of bacteria, as you can see in the left, for the different parts of the state of Maryland. And shown here, the abundance of Acinetobacter baumannii, and in another part of Maryland, in Salisbury, Maryland, Klebsiella ammonia peaked at a certain period. As you can see on the left side, the peak in that particular area of Maryland. And so this allowed us also to monitor antibiotic resistance in these communities. The point I would like to make is that this turns out, this sewage testing technique, to be a public health tool of great advantage. And in the ability to be able to type the virus, we've been able to determine early warning of the appearance of variants of the COVID virus in the community. And here's an example. In Mount St. Mary's University, which provided a case study, we have been sampling twice a week for the last several months. And we found that in one dormitory, the wastewater was positive for the virus. And immediately, the students in the dormitory were tested. 10 were positive, 9 of those 10 were asymptomatic. And they were able then to quarantine the students who were positive and prevent a spread to the entire campus. So the university did not have to shut down, but simply quarantine the one dormitory. One other aspect that I find very exciting is that we've used the model for predicting cholera. By modifying the model, we can predict on a county-by-county basis COVID-19 risk for the United States, county by county. On the left, you can see for April, May 2020, that was the risk map we had produced. And on the right is the actual overlay map of cases that occurred during that period of time. So again, our model this time modified to include humidity, dew point temperatures, movement and tracking using cell phone data, as well as satellite movement of population data, along with the other parameters that have proven successful, allows us to make this kind of prediction. The latest prediction for the United States we made about a month ago, and this, of course, has held up. This is a risk map for COVID. I will close by showing how we can use science to make important decisions. I have told you about the model, computational model, DNA sequencing, highly sophisticated tools. How can we still help the villagers in Bangladesh? Well, since some of the villagers live in boats, such as shown here, others in huts, as you can see, houses, as you can see in the distance, but they use the water, as you can see in the foreground, as their drinking water source. Because we had shown that plankton, zooplankton, carry the Vibrio that causes cholera, it occurred to us that if we could just remove the plankton, we could reduce cholera. And so we did a 3-year study where we trained women, as shown to the left, who would show the women in the village how to use sari cloth folded 4 times, which gives a very good filter to remove the particulate matter, and especially to rinse the sari cloth after use, dry it in the sunlight, which acts as a disinfectant, and then they can refold it, use it again. The water to the right is clear. That is after filtration with sari cloth. And the water on the left is turbid with things swimming in it, which we took no convincing for the women to understand that that really wasn't good for their children, especially babies, to drink. By this application of fundamental science and practical use, we were able to reduce cholera by 50% using the folded sari cloth, which even proved better than nylon mesh, which was very expensive and not available to every family, whereas used sari cloth was. Many students and collaborators from the International Center of Diarrheal Diseases Research, Bangladesh, from the National Institute of Cholera and Enteric Diseases in Calcutta, India, Dr. Nair, Dr. Ramamurthy, Dr. Alam from Bangladesh, and many students from the University of Maryland, postdocs, technical assistants, collaborators from NASA Ames, from other countries, and from other universities. Safe water is a global challenge, and that is why I'm very pleased to speak to this organization today, because you are doing and meeting the challenge of the 21st century to make sure that the next billion individuals on this planet will have access to safe water, which they now do not. Much of this is written in my book that I published just a few months ago, A Lab of One's Own. Thank you very much.
Hello, I'm Patricia Gober, professor of geography at Arizona State University. And I'm very pleased to be here today to talk about my research on water policy. And I'd also like to thank the Prince Sultan bin Abdulaziz for supporting the work that we've done in the Water Prize 2009. I'd like to talk today about the fusion of water science and public policy. As a social scientist, my interests are in decision-making, social learning, and knowledge mobilization. The 15-year effort that I would like to talk about today was funded and initiated by the National Science Foundation in the United States. And the premise for the program that we were funded was that we were looking at climate research, and we were not translating climate research into action and public policy very effectively. And so the National Science Foundation put together an initiative to invite people to come up with new ways of sharing climate science with decision-making so that it will be more effective and lead to actual changes in policy. So the name of the program was Decision-Making Under Uncertainty. How do we make decisions about climate change in the face of inevitable uncertainty about the climate? For us, it meant asking what-if questions. What if particular scenarios of the future were to come to play? What kind of policy change would be important in those situations? We regarded ourselves as a boundary organization in the sense that we would invite both practitioners, water managers, as well as water scientists to come together with us to talk about climate change and how we might better prepare for it in metropolitan Phoenix. The pictures that you're looking at are include the major water modelers in the Western United States on the West, sitting with the water managers in metropolitan Phoenix. And on the right, you look at what we had available to us was a decision theater, a place where we could visualize scenarios and different decisions and decision outcomes for the city of Phoenix. And it was available to us to be able to look at the results of our activities. I ultimately published a book dealing with decision-making under uncertainty in Phoenix and the work that united climate scientists and water managers, calling it Building Resilience for Uncertain Water Futures, published by Palgrave Macmillan. Let me tell you a little bit about Phoenix as a background for the research that we did. Phoenix has about 4.5 million people, and it enjoys a fairly diverse water supply. So it gets water from the Sultan, the Verde River, near immediately upstream from Phoenix. It gets water from the Colorado River, and also it has groundwater. So in times of shortage, of the surface supplies, we've been able to call upon our groundwater sources to support the city. But this picture from the Lake Mead in Hoover Dam on the Colorado River is an everyday reminder of the uncertainty associated with water supply as a result of climate change on the Colorado River. And so this is a wake-up call for Phoenix to take greater foresight, greater action in the future for how to manage its water resources in the face of inevitable uncertainties about the climate and the water supply on the Colorado River, which we see so starkly in this picture. So if climate it's one source of uncertainty about the water security of Phoenix, there are other sources of uncertainty. Projections of growth vary from there will be some 6 million to 9 million. So there's an uncertainty associated with the level of population growth and the water that will be required to support the additional people. There's also this graph which shows the trends in gallons per capita per day water use in the United States after 1950, and it rose quickly until about 1995, and it's been declining ever since. Most people attribute this to more efficient water fixtures and appliances. Whether this trend will continue is a question. So the trends will, I think most of the water managers think that we've pretty much wrung as much efficiency out of the system as is possible, and any further reductions will come from outdoor water use, which is another source of uncertainty, because Phoenix has traditionally been more of an oasis city. It's a desert city, but it uses its water supply for to support rich vegetation as of the sort that you've seen here. Now, the extent to which people are willing to shift to something more like a desert city that we find in the city of Tucson, about 100 miles south of Phoenix, we really don't know the capacity of the population or the predilection of the population to be able to change its water use for outdoor purposes. So that's another uncertainty. The capacity of the population to conserve water to support more growth and under a different lifestyle. So we assert here that we have a problem of deep uncertainty. And problems of deep uncertainty are characterized by fundamental disagreements about the problem at hand, about the probability distributions that define the key variables, and disagreement about what are the best outcomes. What do we want to get out of this problem? So decision scientists characterize this as a problem of deep uncertainty. And we regard the climate change issue in Phoenix as a problem of deep uncertainty. And under these conditions, we ask different sorts of questions than we would ask in a traditional science problem. Problems of deep uncertainty trigger us to ask, what kind of future do we want? And what decisions do we need to make to get there? What's the range of how the future might look? And how do we avoid regrettable outcomes? We're not in the business of optimizing anymore. We're in the business of finding alternatives that will work across a range of futures because we don't know what those futures will be. What ifing? What are the consequences of particular decisions in a complex system? What policies work best across a range of climate futures? What are the costs of delaying decisions, say for another 10 infrastructure decisions for another 10 or 15 years? What are the trade-offs between the costs and the risks of making expenditures that are not necessary? Different kinds of questions than we would ask if we were in a traditional optimization problem. So my research group built a water simulation model that you can see here with our three sources of water, the Verde River immediately north of Phoenix, and the Salt River, the Colorado River, and groundwater. And we use this model to ask questions about the future under different policy choices. The slide you're looking at here looks at policy choices where we've imposed wastewater reclamation at 16%. We can increase that to 30%, to 75%, and we can look at the outcomes for what this means for how much further growth can we support in metropolitan Phoenix. A second policy outcome is to transfer agricultural water on the urban fringe for urban purposes. A third is to ensure environmental flows. And a fourth is to alter per capita water use. So we have these policy levers that we can begin to mix and match to be able to envision different futures that will sustain a sustainable city, that would be able to function and continually grow and prosper for, say, 100 years. We show our decision model with all of the policy levers and all of the outcomes in a decision theater, where we can bring stakeholders and decision makers, stakeholders and scientists together to create new scenarios that decision makers may be more interested in the hopes of implementing the kind of or integrating the kind of science that we produce into their decisions. I just threw in a few more slides to show that I spent 10 years in Canada we implemented very much the same model there, as encouraging a great deal of stakeholder engagement, which you see in this picture, in the hopes of asking the right research questions when we begin to probe the ultimate effects of climate change. We also asked the Canadians what were relevant issues to them, so that we might frame our problems in a variety of ways. What really were they interested in? And one of the as we analyzed their documents and as we analyzed their discourse, we found that stakeholders were very interested in hazards. So we began to try to view many of our problems as hazards, because that's what the decision makers, that's what the stakeholders were interested in. And what did we learn over 15 years in the United States and Canada of working intensely to connect stakeholders and scientists, and climate scientists and stakeholders? What did we learn about what worked to integrate the best climate science into water management decisions? We learned that one-off efforts don't build a common understanding of the problem at hand. A single research project seeking out stakeholders is unlikely to sustain the kind of research effort. It's an ongoing trial and error, and some things work and some things don't. And we learned after 15 years, had a better idea of what was working for us and what wasn't working for us. But the one-off efforts are really not going to get us where we want. Building trust and getting information from people, what they really, how do they make their water decisions? When do they make their water decisions? Who makes their water decisions? And how can we intervene in that process and appropriately with the climate information that we have? Interactivity between scientists and users is absolutely critical to knowledge transfer. Scientists have written articles about the loading dock model of science, that scientists do their work and then throw it off to decision makers and expect them to use it. The interactivity between these two groups over a long period of time, getting to know each other, is crucial in knowledge transfer. We believe that someone needs to own the process of knowledge transfer. In a perfect world, there'll be an expert in the user community who's a water manager who's particularly interested in working with scientists, or there might be an interested scientist who likes to work with decision makers. But ultimately, somebody has to be charged with connecting the best science with the decisions that face us on the ground. So we believe that a boundary organization is necessary to mediate the boundary between science and policy. That boundary organization facilitates social learning between the groups that stands us well when controversies arise. So our group, the Decision Center for a Desert City, always framed itself as a boundary organization. We were sitting with the university's scientists, but also reaching out to the community. That was our job, our first job, and we began to assess the way what worked and what didn't work. So a boundary organization is critical to facilitate this process. We used models to simulate alternative futures, asking what if scenarios. Scientists sometimes make up scenarios that are very arbitrary. We end up with very different scenarios when we ask water managers, what are possible futures that you can see, and how can we integrate those into our models? So to use our models in working with decision makers at the same time to envision these alternative futures. What if we do this? What if we reduce water use by 15%? How much is that going to leeway is that going to give us under certain climate conditions? And we use models to reveal critical trade-offs between lifestyle and growth and conservation and infrastructure. It's always a choice between the decisions are trade-offs. And if we can begin to model those trade-offs and use the science to be able to better understand those trade-offs, we can actually facilitate the decision process on the ground. And finally, the most important lesson we learned that this was a 15-year effort. It took 15 years to build trust, to get to know people, to make mistakes and to recover from those mistakes, to send students out for experience working for internships, working in agencies, and then coming back and informing the science development effort was a way to begin to influence public policy. So with that, I will end my remarks and say that it's easy to do policy research, and it's easy to do, or science is, we can do science work and we can do policy work, but doing work to draw the two groups together and then to evaluate what works and doesn't work was really our goal, and I think laid a groundwork for better climate change, climate adaptation planning in Phoenix. Thank you.